Okay, so what have you guys done so far in randomized algorithms? Can someone give me any pointers? Anyone? Randomized quicksort. Okay. Three coloring. So three coloring. What is the result that you proved?
Monte Carlo last Vegas algorithms. One example of Monte Carlo algorithm, actually last Vegas was given as three coloring. When the graph can be assured to have at least 1/4 of the colorings as three coloring, we have a last Vegas algorithm to find the three coloring.
Okay. Okay. So today my plan is to do something called. So do you guys know what is linear programming? Okay, don't worry, you will see it in today's class. Okay. Okay, so here's the problem. The problem is what is known as max-sat. Okay. So what do you have? You have a set of variables x1 to xn, where the xi's are either 0 or 1. Okay, and you have what are called as literals. So these literals can be like xi or xi bar. Okay. So what is SAT? SAT is basically the problem of satisfiability. So like the other day I was telling you about NP completeness, NP hardness. This is like the quintessential NP complete problem. What is that? You have, let me just talk about CNF SAT. Okay. You have what is known as Boolean formula, okay, in CNF. CNF is conjunctive normal form. So what you will have is a set of clauses, something like xi1 or xi2, okay, xik. So right. So what this means is that this clause is true if at least one of these are true. Okay. So what is xi bar? This. Okay. So let me do this more formally. This is true if xik is 1 and false if it's 0. But this is what is called a negated literal. So this is true if it is 0 and false. What is this? 0 and false if the corresponding variable is 1. Okay, so you have these literals, you want one of these to be, at least one of these to be 1, and by 1 I mean in this case it's xi2 bar, which is 1, which means xi2 is 0. Right. So this is what is known as a clause. And in conjunctive normal form, what you will have is a conjunction of clauses. Okay? So you will have some clause, say C1 and something C2, Cm. Right. So what you have is m clauses in n variables, and the SAT problem is to determine if there is an assignment of values to the variables, okay, some function from x to okay, is there an assignment? So x is the set of the xi's, and is there a function? So this is like a truth assignment. Okay. So is there a truth assignment which will make this formula true? Does there exist a truth assignment such that f holds true? Okay. So this is a question in logic, but this can be translated to almost any graph theoretic problem or any kind of other problem in many areas. Okay. Right. So the SAT problem is known to be NP complete. So have you had a formal lecture on NP completeness and related stuff? No. Okay. It's really not my the topic of this lecture, but something you need to understand these. So I gave some brief idea in the previous class, like what is NP completeness. You can think of it as saying that this SAT, you have a trivial algorithm which will take exponential time. What is that algorithm? Why don't you try all possible assignments to the n variables, right? You have 2 to the n assignments. If you try each assignment, you'll surely know whether this can be satisfied or not. So, but this takes time which is exponential. So what you want to do is to find an algorithm which would take polynomial time. But this is like really hard, and although it's open to prove whether such an algorithm exists or whether no such algorithm can exist, nobody has been able to prove it either way, but we don't believe that an algorithm like this could exist, okay, which would solve SAT in polynomial time. So what is the next best thing that people would like to do is to come up with some kind of approximation algorithms. So there are various approaches, and one of the approaches is approximation algorithms. But how to approximate SAT? I mean, SAT is either satisfiable or not satisfiable, right? I mean, it doesn't make sense to talk about approximations. So the other day I was talking about the clique problem. The clique problem, it makes sense to talk about approximations. Or if you have something like a coloring problem, you want to color a graph using k colors, it makes sense to talk about approximation. Can you do it using say k square colors, or let's say k times log n colors? But here it's either yes or no. So how would you? So one idea is, which people have used, is this max SAT. Okay, MaxSat asks, okay, it doesn't ask does there exist. What it asks is what is the maximum number of satisfiable clauses in this Boolean formula f. Okay, that's the problem. So if you see that if the maximum number is m, then you know that it is satisfiable. If the maximum number is not m, then you know that it's not satisfiable. So if you could prove, if you could find the answer of this problem, you could find the answer of this problem, right? So again, this is not, okay, so it's a technical difference to say that this is NP hard. We say NP complete when it's a decision problem, that is a problem which has a yes or no answer. And we say NP hard when the problem is an optimization problem, as in you want to find the maximum or the minimum of some quantity. So it's only a technical difference, but so this is again NP hard, right? Because if this were not NP hard, then obviously you could do SAT. So right, but this can have an approximation algorithm. Okay? Suppose so what would you think is an approximation algorithm, approximation problem for this approximation version of this problem? What would it be like? See, the clique problem was something like if you have a clique of size, if the largest clique is of size some k, you want to find a clique which is of size at least half k, or k by log n or something like that. So that was again a maximization problem. If you look at coloring, you say if the optimal coloring requires k colors, then you want a coloring which requires let's say 2k or something like, let's say log n times k or n to the epsilon times k. Okay, so what would you, but that's a minimization problem, right? You want to use as few colors as possible, but you can't find an algorithm which uses k colors, so you go for k times something. In the maximization case, you can't find the largest clique or whatever, you go for something which is less than that. So what would you go for in this problem? No, I'm not asking for a solution, I'm asking for a problem. Okay, what I want is, I want an approximation version of this problem. So I want the max, instead of wanting the maximum number of satisfiable clauses, what should I look for in an approximation version?
Let's say alpha is a constant greater than 1, I want it to be like at least maximum.
Yeah, exactly. So that's right. Or you can take alpha to be 1 and say alpha times m or whatever. So suppose by m I mean m's the optimal solution. So the approximation version would say that does there exist a polynomial time algorithm which given f and alpha outputs alpha approximation of max sat. Right. So that's the problem. Okay. So what this means is, suppose the optimal solution which is the maximum number of satisfiable clauses, okay, has something like m star clauses. Okay, so at best you can hope to satisfy m star clauses. Then you want to find we need to find a solution. By solution I mean a truth. Okay, let's call it an assignment, truth assignment. That satisfies how many? Alpha times m star clauses. Alpha. So we are given some alpha which is less than 1, and we want to find an assignment that satisfies alpha times m star clauses. Okay. Right. So that's the problem. I hope you at least got the problem, not the, yeah. So right. So as the topic of the lecture suggests, this algorithm is not going to be a deterministic algorithm, it will be a randomized thing. So okay, so any ideas, any clues? Or any suggestions? Okay, so one thing which you'll probably get used to this when you do more of the probabilistic method or such things, is when you don't know anything about a problem, you just try a completely random solution. Okay. So what would be a completely random choice here? So what is the solution space? It's the space of all assignments of this to 0 and 1, right? So what would be like a completely random point of that space? You just assign every variable to 0 or 1 with probability half, right? So then what is the chance that you come up with a nice clause? What is the probability, a nice truth assignment? You got a truth assignment in this way, right? So what is the chance that you got a nice truth assignment? As in, how many? Sorry? Why do you say that? Divide by number of clauses, as in? Okay, what I'm saying is you took a random truth assignment. Now, what kind of result do you hope that it will give you? Like, how many clauses do you hope that get satisfied? Okay, let's put it that way. Okay, what is the probability? So firstly you would look, maybe you are really lucky and you come up with the optimal number of clauses, right? But that's like really unlikely, right? But what is the chance that you have a nice number of clauses which get satisfied? Something like, for some value of alpha, can you say that alpha m star clauses will get satisfied? So the idea is, okay, this is how it goes. you look at a clause, okay, some clause ci. It has some variables xi1 or let's say xi5 or whatever, bar, right? Now x, okay, whatever. So, right. What is the probability that this clause gets satisfied? Suppose it has some k literals. Okay. What is the probability that the clause doesn't get satisfied? 1 by 2 power k, right? So, the probability that this random assignment, let's call it fr, r for random. So the probability that fr doesn't satisfy ci is 1 by 2 power k, because you need every single assignment to be wrong, right? If any of them hits the right button, then you will be done. So the probability that it doesn't satisfy is 1 by c power k. So the probability that it does satisfy is 1 minus that, right? And okay, so here's something from probability that you might have encountered earlier. It's called linearity of expectation. So how many people know about it? Linearity of expectation. Okay, so anyone with a basic course in probability should know this. Linearity of expectation. So what I'm going to do is to every clause, okay, I assign a random variable. Let's call it yi. So to the clause ci, I assign a random variable yi. Now this variable will take the value 1 if ci is satisfied and 0 otherwise. Okay. So what is the probability? So this basically says that the probability yi is 0 is 1 by 2 power k, and probability yi is 1 minus that. So what is, so let me state it. So yi is 1 if the random assignment satisfies ci and 0 otherwise. Okay, right? So what is the expected value of yi now? Okay, so tell me that. What is the expected value of yi? Exactly. It's only the probability that it's 1, right? So this is, so far everybody is on board, right? Because I hope. Okay. So far so good. Now, okay. So what would be the total number of clauses that get satisfied? It's just summation yi, right? This is the total number of clauses that get satisfied. And that's it. We are counting the number of clauses that get satisfied. So what is the expectation of y? This is where you use linearity of expectation. So all the hints are there now. I mean, Sorry? Yeah, you were saying? Yeah, and each of the individual expectations are equal, so when you add equal things, it's just multiplication, right? So it's just this. That's all it is, right? Okay. Yeah, that's a good point. So what I need to assume is that every clause has at least k literals. Okay. In that case, what would happen is this would be at most 1 by 2 power k, because if it increases, it's, I mean, if k increases, this quantity decreases, right? So it's at most this, so this is at least that, and therefore you get that the expectation here is at least this one, and this is again at least. But you are right. So this will hold only if every clause has k literals, but so right. So let's make the change at this point. You see where you see why I only need to change, because I can assume that the clause Ci had k literals, but yeah, the other clauses might have more. But what is the minimum value of k? What is the minimum value that k can take? It's 1, right? So what this means is that the expected number of satisfied clauses is at least 1 minus 1 by 2 times. Okay. So the what it says is that m by 2 clauses are satisfied. So what does this mean in terms of what we did the other day? What does it mean? As in, what can you surely say based on the expectation? If the expectation is a certain value, you know that there is a point in the probability space, right, which is the expectation. So from this, what you can say is that there exists Fr such that if you right, how should I say, Fr applied to this, which means when I give the assignments according to Fr, at least m by 2 clauses get satisfied. Okay. Right. Okay, so far so good. So what does it mean in terms of an algorithm? What it means is this is like an existential result, okay, but you could translate this into an algorithm, a randomized algorithm, just by executing the proof. Okay, so your proof will just do your algorithm will do exactly what the proof does, right? You take a random assignment and you see that if you don't have m by 2, then you can repeat, and what this expected number means that by repeating a very few number of times, you will get an assignment which has m by 2 satisfying clauses. Okay, right. So yeah, you need to know some more inequalities to show that you will not have to repeat too many times, but you can think of it as something like the coin tosses that we did the other day. See, you keep tossing a coin until you receive something like a head followed by a tail. It's always possible that you will have an infinite number of tosses, but generally what will happen? You will, in a few number of tosses, you will right. So So this is one particular way of doing it. And the nice thing is okay, this algorithm is randomized, but you could also de-randomize it. As in, you could come up with a deterministic solution which will not need any coin tosses. How is that? Okay, so it's called the method of conditional probabilities. So intuitionally it's very simple. I mean, if I give the idea to you, you will find it easy to prove it. The idea is, you look at a literal, you count the number of clauses that get satisfied when that literal is 1, then you again count the number of clauses that get satisfied when the literal is 0, you take the maximum. Okay, you go with the maximum. If more clauses are satisfied when the literal is 1, you assign it to 1. If more clauses are satisfied when it's 0, you assign it to that. And you notice that the one of these numbers will be at least m by 2, right? Because if k clauses get satisfied when you make it when you make a literal 1, then m minus k must get satisfied when you make it 0. So one of these numbers is always n by 2, and that way you can show that. So you don't need to toss coins, you can actually go by a fixed procedure. Okay.
What if the literal doesn't appear in the class?
Yeah, that is another, but then right, but what you can say is, if the literal appears in some mk clauses, at least half of mk will, satisfy. So you can prove it formally. Okay, right. Okay, but what if you want to do better? What this means is, this means for this problem is, okay, so I need to tell the connection between this and the previous thing. So what this means is, see, what is the maximum number of clauses? It is at least, okay, it is at most m, right? And you have satisfied m by 2 clauses already, which means that you have at least a 2-factor solution, right? As in, what is called a half, at least half the optimum number have been satisfied. You see, if the optimum number is m star, then you know that m star is less than, okay, so that's it. What it means is that you have satisfied at least half the optimal number of clauses. So this idea gives you a 2-factor approximation algorithm. Okay, but what if you want to do better? So notice that, notice one thing, this is not actually m by 2, it's summation 1 by summation over I, let's say something like ki and so on, right? This is actually, so right, it's something like this. Right, that's the real expectation, the real value of the expectation. So what this means is, in the worst case you had ki to be 1. Suppose you were given that ki is at least 2 for every clause, then you would get a 3 by 4 kind of approximation, right? Because it will be like 1 by 4, so you get a 3 by 4 m would get satisfied, you get a 3 by 4 approximation. So right, so the real problem is when you have clauses which satisfy, which have only one variable, that's the bottleneck, right? Okay, so now I'm going to tell about a different algorithm which is specially catered to the case when there are clauses, when there are many clauses which have just one variable. Okay, right. And to do that I need to maybe build up some kind of, and this is okay. So this is something like a general technique. Okay, both these techniques are general, and they can, you know, be adapted to other problems, which is why they are the topic of this lecture. Okay, so this technique is what is known as LP plus randomized rounding. Okay, so this approach, okay, so linear programming, not many people know, but linear programming, okay, so linear programming is something very different from the computer programming that you might have done so far. This is what is called mathematical programming, okay, it's something completely different. So what you have is you model this problem. You had this problem which was based on, it's essentially a logic problem. You model it as a mathematical system of equations, and then what you want to do is you want to find a point in the space of these variables which would satisfy all these equations. Okay, so how do you model this as a system of equations? How do you do that? Okay, so one idea is as follows. You have these xi's, okay, and okay, so actually I should have said something like true or false, but I made it slightly easier. It's 0 or 1. So here it's again 0 or 1, okay, and right, what you have is for every clause, this clause will go to something like summation. Okay, so let me call this yi, so that so this is like a number. This is not a logic variable, it's a number now. Think of it as a number. Okay, this is summation yi. This is okay, sorry, yj. All the j's such that is j such that okay. So if the variable xi appears as xi in cj in ci, okay, if the variable, so look at the variable xj, if it appears as, okay, if it appears as xj, you take yj, okay, and if it appears as xj bar, then you take 1 minus yj, okay, right, and what you are saying is that this sum is at least 1. That's what it means to say that the clause ci is satisfied, right, and what we want to count were the number of clauses which get satisfied, okay. So again I'll do something like what I did there. I'll call this zj, zi, sorry, zi, right, right. So zi's are also something, but zi's will go from z1 to zm, whereas yi's will go from y1 to yn. Let me call this zj or something. Anyway, I in n and j in m, okay, right. And now what is the number of, so what is the problem that you want to solve is that's maximize this sum, okay. right? So this is an example of what is called linear programming. You have a system of constraints, so there will be like m such constraints, one for each clause, and you have um, an objective function which you want to maximize or minimize, as the case may be. Okay, right. And this kind of problem is, so you see that you could translate, for example, the original SAT problem to this. Okay, so if you could do this kind of problem in polynomial time, then again you would be able to do SAT in polynomial time, which is highly unlikely. So this is what is known as integer linear programming. Okay. ILP. Okay. Yeah, yeah.
But I might not, I might get the evaluation mode like this function, this expression C is
Right.
equal to, might evaluate the value greater than 1.
Yeah. So
If I try to maximize over it, I might get an answer. Because I might have some of the ZX to be far greater than 1 and everything else is 0.
no, it doesn't say that it doesn't say that Zi is the sum of these things. I only need that this is right. Right. So yeah. Yeah, so when you formulate this kind of a problem, you need to be careful as to whether all the constraints are modeled exactly or not. So you are right in this, you have to check whether everything is, you know, modeled satisfactorily or not. Okay, in fact I am not sure about this, right. If this is,
If this evaluates to 0, then Z is 1. If it is greater than or equal to 1, then Z is 1.
yeah, aha, if this evaluates to 0, then Zi must be 0,
If it is 0, then Z is 0. If it is greater,
otherwise it's 1. But Zi can still be 0, but yeah, Zi can still be 0, but then you could change Zi to 1 and that would give a better maximum, right.
Z is taking values 0 and 1.
Yeah, you see if this is more than 0, this can still be 0, that will satisfy the constraints, but then you want to maximize this, so it's better to have this as 1, right. Right. So that's the randomized that's the LP program, and what you know is that so that's the integer linear programming, and what you know is that it's NP hard to solve this in polynomial time, right. So then what you do is, so this is the next part. Okay, sorry, okay, it's not the next part, it's the part after this. So the second part is, you allow these yi's to take real values, the yi's and the zi's to take real values. So all you need is yi is greater than equal 0. Okay, so something like, let's say yi, it's in the closed interval, and similarly okay. and this, so this has polynomial time solutions. This kind of thing can be solved in polynomial time now. The same problem, but when you allow real values instead of integral values, it's much easier. So, so this is like a typical thing. You have a problem on a continuous space. You find that there are techniques to solve it. You move over to the discrete space, and suddenly this problem becomes very hard. It's like, you know, something like integration versus counting the number of lattice points. So something like, I mean, it's just another example. If you want to, if you have this curve and you want to find this area, you can just integrate the curve, right? But if I say you want to find the number of grid points that lie exactly inside, for example, this one is inside and this one may be outside, something like that, then it becomes quite difficult, right, for an arbitrary curve. So similarly, I mean, the details are completely different maybe, but the idea is that problem can be easy in continuous space, but it might become quite difficult when you go over to discrete spaces. So yeah, so this is hard, this is NP hard, okay. So all you have succeeded in doing here is expressing one a problem in one language, in the language of logic, to a problem in a different language, okay, the problem of the language of numbers, and it remains NP hard. It should remain, right, because changing language should not change the hardness level. But now what you can do is you can relax this integer linear to just linear over the reals, okay, and this has solutions. So you can solve the LP in polynomial time. Right. Okay. So far so good. So now you have some solutions. Let's call them yi cap and zi cap. Okay. So these are the solutions to LP. Okay, to the LP. Okay, so this is like, let's call it 1 and let's call this 2. And let's call this 3. Okay, right. So you will get some optimum value of clauses which get satisfied, but you know that now you are like considering fractional or real values, okay, but so that solution doesn't really translate back to the integral case, right? But what can you say when you compare those two solutions? By those two I mean the optimal solution, let's say m star, and the solution that you got, which was, let's say, m cap. So suppose you compare m star and m cap, what can you say about these two? Can you compare them at all? Okay, so notice one thing, that the integral solution is a real solution, but the real solution need not be an integral solution, right. So, and you are maximizing over all real solutions, so it means that you are maximizing in particular over this solution as well, right. So what you can say is that the solution that you get, the value that you get will be at least as good as the value that you could have got if you were to solve the integral problem. So what this means is that this any questions? So everything is clear then, right, because this is an integral solution which is also a real solution, so this is going to be at least as much as that, right. So yeah, so what can we do now? We have a nice solution, in fact we have better than what even the best solution, okay, but this has some values of yi's which are fractions, right, something between 0 and 1, a real number, or yeah, let's just say a real number between 0 and 1. From that, how do we go to 0 or to 1? We need to find some way of going from something in between to either end. How do we do that? Yeah, one idea is to use a threshold, that's a nice idea, but the idea that we will be looking at is what is called randomized rounding, okay. As threshold works in certain cases, and of course it will work in every case, the only difference is you need to analyze and to see, like, you know, what kind of solution you get. You want a good approximation solution, so what kind of approximation will the threshold give you? You need to come up with a good threshold and so on. But what this will give you is something which is the best possible on expectation. Why is that? So yeah, let's see. So okay, this is the last step as far as the algorithm is concerned. Okay, I will set yi, okay, to 1 with probability this is kind of cool, isn't it? Like you take a real value between 0 and 1 and you make it 1 with this probability, right? Of course 0 with the 1 minus yi cap. Okay, so what is the expected number of clauses that get satisfied? Now it will be equal to this. Why is that? Because you see right, okay, let's see, so this is the algorithm, okay. This is the second part of the thing where you took linear programming, you relaxed it, you solved the relaxed program, and then you did what is known as randomized rounding, okay, right. Right. So now what you need to do is to analyze this and to show that this procedure will give a good result. So how would you analyze this? Again, so what you do is you look at an individual clause, okay, and you do the same thing as we were doing earlier. We ask the question, okay, what is the probability that these xi's or whatever whatever, let's call this assignment FR, FR star or whatever, FR star does not satisfy Ci. So what's this probability? It's the probability that all of these, okay, so here I'll make a small change, which is I will think of all these literals as being, you know, positive literals rather than being negative. So if I had a an xi bar somewhere, I will call it some, you know, xn plus 1 in the positive sense rather than, you know, thinking of it as a negative literal. So you can think of all literals as being positive, and now what is the probability that does not satisfy Ci? It is basically, so what's the thing? Everything goes wrong, right? It's the probability all I. All I in, okay, all yi in, okay, let's call this j, yj, ci, right? This is the probability with which everything goes wrong. So your clause is not satisfied, right? So the probability with which it is satisfied is something like this. Right, and right, so then you can do something like what we did earlier, take those so these kind of random variables are called indicator random variables, because they just indicate whether something is 0 or 1. So you can again take these indicator random variables and get okay, so you can again get take indicator random variables corresponding to the clauses, and you get the expected number of clauses which are satisfied. Okay, so that will be something like this, summation this over i's going from 1 to m, right? So okay, so you have satisfied a lot of clauses, right? So let's do some more analysis on this. I mean, what does this mean really? Okay, so number of satisfied clauses on expectation, okay, expected number of satisfied clauses, this is what I had, right? And this was something like this, right? Right. So what is the minimum value that this can take? Okay, what is the minimum value that this can take? If I take, so some, let's call that minimum value, let's say y min, okay, then I can say that this value is at least y min times m. right? If I find the minimum of this over all these possible over all possible values of yj hat, then this expectation is surely the minimum times m, right? So how do I get the minimum? Okay, so it's something like this. You have certain variables whose zi, so they will be minimum. Okay, subtracting one from it. Okay, so they will be minimum when this is maximum, right? The product is maximum. And when will the product be maximum? When the sum is guaranteed, when the sum you take has as a certain lower bound and you want the product to be maximum, when does that happen? When they are equal, right? So therefore this will be minimum when all the yj's are equal, and you can take that value to be what is that? The sum is guaranteed to be zj, right? So suppose there are k suppose there are k variables, then the minimum will be, so yeah, so let's write it here. So y min is at least 1 minus 1 by 1 minus k raised to b, right? This happens when they are all equal. You have k things which sum to at least 1, right? So they will be when they are when they are equal, each of them will take the value 1 by k, right? So then what you get is the expected number of satisfied clauses is surely this. Right, right, and what you can show is that this number is it's at most 1 by e, okay, this number. Why is that? Because I'm sure you know this, you take limit 1 minus or yeah, you know this is 1 by e, right? And this approaches the limit from above, as in it's always greater than 1 by e and it slowly goes to 1 by e. Wait a minute, sorry, it's always less than 1 by e, yeah, and yeah, you can just check by expanding, it's always less than 1 by e, so this will be always greater than 1 minus 1 by e, right? So what this means is you have got another approximation algorithm which gives a 1 minus 1 by e factor approximation, which is slightly better than half, okay. Right. So you have got now two algorithms, and what you want to do is to see the trade-off, okay. Like this algorithm was quite simple, but the bottleneck was when k equal to 1, that was the bottleneck, and this algorithm is slightly more complicated, but it does not have any bottlenecks, it gives a nicer lower bound. But can you do a trade-off between these two? Okay. So the actual lower bound that you get is this. right, and this is like this will be much better than this for small values. Okay, let's say you take k to be 1, you take k to be 1, you get m, right. You see how this goes. If you take k to be 1 here, you will get m. If you take k to be 2, you will get something slightly less than m, and eventually this will approach this value, which is like 2/3, but for small values it works much better, right, and that one doesn't work so well for small values, it works well for larger values. Okay, you see this point. This right, so when k equal to 1 this is m, when k equal to 2 this is maybe 0.9 m or something, and it keeps going down to 2/3, whereas this is half when k equal to m, k equal to 1, and this becomes better and better as k increases, right. So can you do something like a trade off between these two? That's the last thing. Okay, can you do a trade off between these two and achieve something better than m by 2 or even that one, 1 minus 1 by e times m? And so the idea is you do both of these and you pick the better value. You look at both these solutions and you pick whichever is the better, right, that's simple enough. But can you prove that that will surely give something better than this, both of these individually? Okay, that's the next thing. So let me do a summary. We looked at algorithm 1, we looked at uniformly and randomly. We chose some point in the probability space and and the second algorithm, so this, okay, so this gave you a 2-factor approximation. Okay. Okay. The second algorithm was you did some fairly complicated stuff. You wrote down an ILP, changed it into an LP, relaxed it into LP, you solved the LP, and this is this is fairly complicated. Okay, this is not easy. I mean, I didn't even talk about it, I just said that you can do it, but you need some fairly good heavy machinery to do this. Okay, so there is one easy method, this Karmaker's algorithm, but it is not known to be, in the worst case it could be exponential time, but there's the other more difficult method, which is ellipsoidal method. That's known to be polynomial time, but it's so complicated that in practice the exponential time actually takes it's easier to implement and it works faster. But anyway, you do somehow, okay, you take either one of those or whatever you want, you solve the LP, and you finally you do randomized rounding. Right. So the basic thing was, and now the bigger picture is you do both of these and you look at the best solution, okay. You take the best answer from okay, so that's what you do. Now what can you show? Can you show that you will get something which is surely better than either of these individually? Right, and it's again based on these expected values, the expectation. What you can show is, so suppose you get something like, so let me call this as M2 star, and oh okay, sorry, this is the optimal, this is the optimal. Suppose I call the first value as N1, this is the output of algorithm A, and suppose I call the second value as N2, this is the output of algorithm B. So my final algorithm outputs what? The max of N1 and N2, right? Now, right, so what can I say about the max of N1 and N2? So as it turns out, I can say something like this is at least 3 by 4 times, okay, that's the nice thing. And if you do a trade off here, then I think you will see, you take k equal to 2, what you get is 1 by 4, right? So this is 3 by 4m, then k equal to 2, this becomes 3m by 4. You take k equal to 2 there, you will again get 3 by 4m, right? So this is coming down from m to 3 by 4m to eventually this value, and that is going up, right? So it seems like 2 is the right point where you can do a trade off, and apparently you can show formally that 2 is, you will get this value. So how do you do that? It's by taking these expectations, as I said. What you can show is, you look at the average, okay, you will be able to show that the average is at least, so it suffices to prove that the average is at least 3 by 4, okay, and to show that, all you need to do is to show that this is at least 3 by 2, right? Right, so what is either of these? This was actually, okay, what was this? This was summation over the clauses 1 minus 1 by 2 power ki right? And what was this? This was summation 1 minus, okay, 1 minus ki raised to ki, again summation over I, right? Right, and now what you can do is you combine them, you get 2 minus 1 by 2 power ki, right, minus 1 minus 1 by ki raised to ki, okay. And this you will be able to show is at least 3 by 2 times m. Why is that? Because you take individual an individual summand, okay, you can show the individual summand is always 3 by 2, at least 3 by 2, right. So what is the individual summand? It's just, you can show this right, 1 minus 1 by ki raised to ki. Okay, so yeah, this is not so hard to show, okay. Once you show this, you are pretty much done, and this is just some mathematical manipulation that all of you guys can do, I'm sure, right. So right, so that's right. So what we did was we saw a crude, a simple yet effective randomized algorithm. We saw a more sophisticated algorithm, and in the course of that we also saw what is an integer linear programming problem. We saw how it can be relaxed to an LP. Okay, I didn't dwell on this much about how you solve the LP. There's a lot of literature on that. There are two major techniques, as I told you, like right, and finally, but this you can, so we took this as a black box, okay, we didn't really solve it, I just told you that you can do this. Finally we applied randomized rounding, and and the other thing which is not part of the algorithm is the analysis of the algorithm, okay. So we also analyzed all these algorithms, and right, and we saw that we can get an approximation which is a, what is it, 4 by 3 factor approximation for the MaxSat problem, okay. So that's it, and you guys have my email and you know my room, of course, so any questions or comments or feedback, you're most welcome. Okay, so that's it.